Alright, last video of the day on circuits. We're going to have to fight the announcements on this one because I'm doing it at the end of the day, so I apologize to no one's going to watch it anyways. Circuits. A circuit is the complete path that the electrons follow. In Europe they call racing track circuits because it's the path that the cars are going to follow. This is called a circuit because it's the path that the electrons are going to follow. There's at least three parts to all circuits. You have to have some kind of voltage source, sometimes called an EMF, or a source of electromotive force. A conductor, which is the path that it's going to follow. And a load, that is what is going to use our electricity. The voltage source, think of it as the push. It's what moves the electrons through the circuit. Voltage is potential energy. It's a measure of how strong the push is behind the electrons. A AAA battery is a 1.5 volt battery. It has 1.5 volts worth of push. A 9 volt battery has 9 volts worth of push. It will push a lot harder.
Garber, please report to the Cougar Plaza for pickup. Samantha Garber, please report to Cougar Plaza for pickup.
Voltage sources can be alternating or direct. Again, we saw that in one of our recent videos. Direct current coming from the batteries, alternating current coming from the outlets. So this is the push. This is what moves the electrons along. The conductor is the path that they're going to follow, and oftentimes it's wire. Sometimes it's on a circuit board, in which case we call it a trace. You can see between all these little solder points, there's like little pathways. These are pieces of metal that are actually laid right down on the circuit board. This is the path that the electrons follow in this type of circuit. You got to have something to push the electrons along. You have to have something that the electrons can follow when they're pushed along. And you have to have something that uses that energy, something that uses the energy the electrons have. We call that a load. Loads can be many different things. I have three of them up here on the board. This being a light bulb. This load uses the electrical energy to produce light and heat. An electric motor. Electric motors use electricity to produce mechanical energy. And these are resistors. Resistors use electrical energy to produce heat. If you don't have a voltage source, the electrons don't move. Nothing happens. If you don't have a conductor, the electrons have nowhere to go. They stay put in the battery. Nothing happens. If you don't have a load, you actually have a dangerous situation called a short circuit. If there's nothing there to use the electrical energy, the electrons flow out of control, which, because of resistance, can cause the circuit to overheat and cause a fire. The circuit breakers in a house, the fuse box in a house, the fuses in a car are all designed to prevent the kind of damage that you can see from out of control electricity and that heat that can produce. So again, voltage source, a path to follow, and something to use the electricity. That's what you need for a complete circuit. Most circuits are represented using circuit diagrams. They're kind of like road maps for a circuit. It shows us how the electrons are going to move around, what the electrons are going to flow through. And circuit diagrams are written using circuit symbols. It's a universal means of writing down what you're looking at so that everybody is on the same page. Everybody knows the same thing. And these are some of the common circuit diagram symbols. A short line and a long line, that represents a cell, like a button cell that you'd find in a watch. Two or more of those, you've got yourself a battery. Kind of compare it to cannons. If you have a cannon, you have a cannon. If you have a whole bunch of cannons, you have a battery of cannons. Battery means more than one. A switch kind of looks like a little drawbridge. This switch is drawn in the open position. This position will be off. If we had two dots here and drew it as a horizontal line, it would be a switch in the closed position and it would be on. Circle with a V, that's a voltmeter. That measures the voltage. That measures the push. The circle with the A in it is an ammeter. That measures amps or current flow, the kinetic energy in the system. This one measures potential, that one measures kinetic. The zigzag line is a resistor, one of those things that turns electrical energy into heat. A variable resistor, that's kind of like a dimmer switch. It can adjust how much resistance it has, a little or a lot, depending upon how it's set up. And the last one on here is a lamp. It's a circle with a little curly line inside to represent the filament and light bulb.
Cobb, please call extension 6201. Ms. Cobb, please call extension 6201.
These are two examples of circuit diagrams, simple little circuits. Here we see our battery in our circuit. This tells us we have 3 cells. We see the 3 long lines, 3 short lines. There are 3 cells there. The electrons flow out of the battery through a switch. And again, the switch is drawn in the open position here. Then they'll flow through a resistor, the jagged line, the zigzag line. And then they're flowing through a lamp, again the circle with the curly line inside, back to the battery again. Again, another example of a circuit diagram. Again, we have a battery. 3 long lines, 3 short lines means we have 3 cells in that battery. The electrons flow out of the battery and either through a lamp or a resistor. They split here and go one way or the other. We have a lamp, we have a resistor, we have our switch over here, and then back to the battery again. Again, you need to be able to read them. You need to know what the symbols mean so that you can interpret the circuit diagram. Circuits come in 2 types. There are series and parallel. They relate to the number of paths the electrons have to follow. If we look back to the 2 circuit diagrams that we just had, in this first one, when they left the battery, there's only one way around to get back to the battery again. In this one, we had that Y in the road. We had that split. The electrons went through either the bulb or the resistor, not through both. It was one way or the other. One of those is a series circuit. The other one is a parallel circuit. The one with a single path is series. Any circuit with 2 or more paths is parallel. Here's an example of another series circuit. We have a battery here, 2 cells, hooked up to 2 light bulbs. This is what the circuit diagram would look like. Here's our 2 batteries, or 2 cells. Long line, short line, long line, short line, 2 cells. Flowing out through bulb number 1, then through bulb number 2, and then back into our battery again. There's only one way around this circuit. That's how we know it's a series circuit. Here's an example of a parallel circuit, another example of a parallel circuit. Again, a battery containing 2 cells and 2 bulbs wired in parallel. And here we can see the electrons will flow out, they will reach this point, and they will either go through the first bulb or the second bulb, but not through both. We have 2 paths. We can go through the first bulb to get back to the battery. We can go through the second bulb to get back to the battery. 2 different paths means it's a parallel circuit. Pretty easy to identify because usually when you draw them, you set up parallel lines. And you put everything between those parallel lines. Series and parallel circuits have advantages and disadvantages. For the series circuit, we divide the voltage up. That's kind of a disadvantage. If we have a 9-volt battery and we have 3 things on the series circuit, each one only gets 3 volts. We have to take the 9 volts divided by the 3 loads. Each one only gets 3 volts of potential. Another disadvantage of these things, when one bulb goes out, they all go out. It's like the cheap Christmas tree lights. Because the voltage is being divided up, we also tend to see, if it's a circuit involving light bulbs like the one that I just showed you, dimmer bulbs. Lower voltage means dimmer bulbs. We take that 9-volt battery and have to divide it up by everything. Each one only gets a fraction of the available potential, so we end up with much dimmer lights. The advantage? Easier to make. That's why the cheap Christmas lights are so cheap. They're easier to make than a parallel circuit. They take less wire than a parallel circuit, so they tend to be more cost effective. They tend to be cheaper. Parallel circuits, advantages of that, when one bulb goes out, the others stay on. If we have 3 bulbs wired together in parallel and bulb number 1 goes out, the electrons can still flow through bulbs 2 and 3. We don't divide the voltage up, so as a result we end up with brighter bulbs. So if we have a 9-volt battery and 3 bulbs, all 3 bulbs get 9 volts. It ends up with much brighter bulbs in the end. Problem is they are more complicated, and because they're more complicated, they tend to be more expensive and harder to make. They do sell expensive Christmas tree bulbs that are wired in parallel, where one bulb goes out, the others stay on. Again, this is the series circuit. These bulbs would be dimmer than these ones in parallel. This would produce the brighter bulb. In parallel, if this bulb goes out, this one stays on. Again, it might not be able to go down this path, but it can go down this one. This is the way our houses are wired. Could you imagine if your house was wired in series? When you turned off the light, the TV would go off too. Our houses are wired in parallel so that we can turn one thing off and leave the other ones on. And here we divide the voltage up. If this is 3 volts coming from our battery, Each one gets 1.5. That's what makes the bulbs dimmer. If this is 3 volts, both get 3 volts. And again, that's why the bulbs will be brighter in parallel. That is your whirlwind tour of circuits, complete with disruptions from announcements. Hope you enjoyed it. If you have questions, make sure you ask.